Ly. So Lx is this and Ly is that. It will be equal to, we will have to write the commutation of these. So the Lx value from here, the Lx value is equal to y pz minus z py, and we are going to find its commutation with Ly, which is z px minus x pc. So these two commutations we will have to work out. Now, one way is to directly multiply them and then put the values and reorder them. The other way is to just do it like this. So I can write that first this one will be calculated with this, and then this will be calculated with this, and again means I calculated this with this, then this with this, then I will have to calculate this one with this one, and then this with this. So this will be equal that first the ypz commutation with zpx. This is one commutation that I will have to do, and then minus sign is here, and the commutation of zpy, I will have to very carefully look at the order of them. Their order shouldn't be jumbled, otherwise they are operators and we will get a wrong result. So zpy with xp, this zpy I will do with zpx. So this is zpy with zpx. zpy with zpx. And then this one with this one, so minus sign will come in, and this is minus, and here this ypz with xpz, ypz with xpz, ypz with xpz, and then minus sign is here and minus is here. So this will become plus, and we will have zpy and xpz, zpy and xpz. So now look to the relation that we have done here. So this thing is equal to, if I look here, to the second term. Now in the second term, first look at this one. This is z here and z here, and px and py are different. I know that px, py, all this can be equal to 0. And here, if the two are the same, Ri, Rj, they are different, then this will be equal to 0. So I can write that these all can commute. I can expand this one as well, but as here is zz, they are commuting, and py and px are commuting with each other. So this thing is equal to 0. Similarly, if I look here to this one, now y and x are commuting with each other, y and x, and pz and pz are commuting with each other. So this one is equal to 0. And so I can write that. Now what's the problem with these two? Why they are not commuting? Because here this one is different from this one and this one, they are different. That's why they will not commute. Here this and this are different, this and this are different. So the different, we will say they are not commuting. So I will go and write them again. So let's see that this is ypz and zpx. So I will have to just expand them and I will write that ypx. So this will be, if I do multiply it, let me do this step and then I will do the second one directly. If I do multiply this one, then this will be ypz times zpx, ypz times zpx, and minus, then it will be zpx times ypz. So I can take common from here. If I take ypx is common, then from here, if I take ypx is common, then I can write that this one, ypx, this y and this px is common. So this is zpz, or I write in order pz into z, minus ypx is common, so zpz is there. And now this one is ypx, but this one I can write is the commutation relation of pz with z. So here, this term, if I take z is common, then py and px, and from here I know py and px, they will commute, so this will go to 0. And from here, if I take pz is common, then y and x are commuting, so these two terms will go to 0. And when I will come here and I have taken already the ypx common, then it is the commutation of pz and z as I did here, and over there I have taken pyx is common, so plus pyx is common, and it is the commutation of z and pz. So this will be equal and pyx. So now I will have to put their values, and I see that from here zpz will be equal to ih bar, and this is pzz, so this will be minus ih bar, and here this is zpx. So this is z and not x but z here, because we are having zpz here. So this will be equal to ih bar. If I take ih bar is common, then I will not take this bracket but this bracket, not to confuse with the commutation. And this is ih bar I have taken as common, this one is plus ih bar, so pyx minus ypx. This is pyx, and Okay, I can write this is x in py. So this is ypx and xpy. So I can write this one. Okay, so this is ih bar, and as this was common, so this is xpy minus ypx, and this is xpy minus ypx, and this is equal to ih bar and lz. So I have proved that lx ly commutation is equal to ih bar and lz. So when here we have x, here we have y, here we will have z. This is also that cyclic order. So I can write that here lx ly, this commutation will be equal to ih bar and lz. Similarly, if I take ly and lz, then this will be ih bar lx, and when this will be lz with lx, then this will be equal to ih bar ly. So these commutations are also cyclic like the previous. Lx will go to ly, ly will go to lz, ly will go to lz, lz will go to lx. Similarly, here lz, so this means x, y, z. This lz will go to lx and lx will go to ly. And it is easy to remember that lx will go to ly. If this commutation is, then this will be lz. Y, z, so x, z, x, and y. So these commutations are like this, and we have proved that there is a cyclic order in them. And now we will go to the similarly in these one, if I want to write the uncertainty, like we were having x in px, we remember this relation, this is ih bar, and then the uncertainty here was that sigma x sigma px, this will be greater or equal to h bar over 2. And this, if I go with this terminology, then I can write that the uncertainty principle for the angular momentum means sigma in Lx with sigma in Ly. This will be greater or equal. Now, these both are actually the uncertainties in Lx and Ly because they are not commuting. Non-commuting operators will cause uncertainty. So this will be h bar over 2 and Lz, Lx and Lz. And this will be the expectation value of Lz and absolute as well. Similarly, as we know that the vector is having, all vectors are having problem in their conservation, and that conservation comes due to the problem of their vectorial nature. For example, I will take the example of momentum. So the momentum, the law of conservation of momentum fails due to the vectorial nature of field. For example, if I throw a piece of mud on this wall, then the mud will stick to it. There was initial momentum and the final momentum is not there. So this is due to the vectorial nature of momentum, or for example, if one P is in this direction, the other P is in this direction, and both are the same and they collide, so both the particles come to rest and the initial momentum is there while the final momentum is not there. So we are having problem with the law of conservation of momentum, or this fails due to the vectorial nature of this, and that's why when the law of conservation of momentum fails, we go to the law of conservation of energy and we take its square. Like we know that the kinetic energy P square by 2m is the kinetic energy. So whenever the law of conservation of our vector fails, then we go to the square of that vector and we take their inner product and it becomes P square, and we call that is energy. P square by 2m, we call this is energy. Now here the law of conservation of momentum will fail in the head-on collision, but the law of conservation of energy will survive. It will not fail. So it is equally important that we calculate L square as well. L dot L, and it is equal to L square. Because if we are having problem with the conservation of the physical quantity, then we will have to go to the square of it, and that's the reason that we go to the scalar form. Like for example, a basic question is that when we know momentum, we can calculate the energy of a body, then what's the need of it? That momentum is there, so what's the need of energy? Means what's the need of inventing another term? The reason for that is that from momentum it fails due to its vectorial nature, so we will have to go to the scalar nature of it and it comes out to be the energy of a body. So we will have to go to the L square as well, the magnitude of angular momentum squared, and we will have to check that what are the commutation relation